Hello and welcome to Project 24008 3D Printing with Mine Tailings. We are sponsored by Auxilium Technology Group. My name is Emilio Rodriguez and I'm the team lead.
I'm Aljuri Hamdan and I'm the procurement lead.
I'm Dylan Krug and I'm the electrical lead.
I'm Osman Sayed and I'm the programming lead.
I'm Aiden Peck, the design lead.
I'm Landry Guerin, I'm the mechanical lead.
We're a second-year project tasked with creating a three-dimensional industrial printer capable of utilizing mine tailings concrete. The previous team's project was improved upon with a complete redesign. We have accomplished synchronized three-dimensional motion, implementing homing switches, and the ability to follow G-code instructions. This furthered last year's project by successful and controllable motion on a larger scale. Tailings are mine waste and leftover material after ore is extracted, similar properties to sand and dirt.
And this is what typically happens to mine tailings. They are left in piles on or by major mine sites. The industry as a whole is currently looking for more sustainable solutions for tailings management. One sustainable solution to tailings management is to produce tailings concrete. Tailings concrete mimics all of the structural properties of normal concrete. Our system will be intended for use directly on mine sites. They can harvest tailings and process them directly on site to produce three-dimensional structures. This is a sustainable way to repurpose mine tailings that also saves the mine time and money. Here we have the system block diagram for our project. As you can see, the Duet 3 main board is directly in the center, powered by a 48-volt power supply connected to 120 VAC outlets. The board powers 5 stepper motors, each coupled to a drive mechanism. We used ball screws for the Z-axis, moving up and down, a ball screw for the Y-axis to move side to side, and racks and pinions for the X-axis to move it back and forth. The Y-axis has a nozzle connected to it for future concrete testing by the sponsor. Duet 3D Web Control is directly interfaced with the board. This is where the engineer can upload G-code print instructions.
We need to make sure our system is used under the right conditions, so it's either indoors or outdoors. If it's outdoors, it needs to be in clear weather, not too hot or too cold, and humidity is low. For boundaries, the weight of each truss shouldn't exceed 50 pounds, and it should be assembled under 1 hour with 2 operators.
Mechanical operation is broken down into our 3 major axes, X, Y, and Z. The printing tolerance themselves is going to be 5 millimeters across all 3 axes, and synchronization across all movements for axes is mandatory. For the vibration within our system, we have our rack and pinion for the base and our ball screw, which are required to help limit that vibration. Our safety measures like limit switches are used to help prevent any damage to the system as it rotates throughout the axes. And lastly, the output of our system, or the print volume, should be 4 feet by 4 feet by 4 feet across in volume.
These are electrical operation requirements. We wanted something easy to find or bring to a mine site, so we are utilizing a 120 volt outlet or the compatibility with a 120 volt generator. What that's going to do is it's going to power a DC external power supply that goes from 11 volts to 48 volts, but that 48 volts is specifically what we need for our Duet 3D motor control board to power our 5 motors and all of our sensors and equipment. We wanted something easy to use or interface with some untrained operators, so we went with the wireless interface. Also something that was open source, utilizing that Duet 3D mainboard. And what that's going to do is we can go to their website and upload those links once we establish an IP connection. Here's our system software operation requirements, which kind of pointed us in the direction of this motor control board, specifically the Duet 3D 6HC model. We wanted something that the user can input G-code commands via their website and directly connect it to the board, which is exactly what this does. We also wanted something that would indicate an error, that way the print doesn't fail, especially when utilizing concrete or in an industrial environment. So we have LEDs to alert that, and then we're also going to have limit switches to provide inputs to tell us when our system has been homed, allowing for a known location whenever we start up the machine.
These are the models for our system. This includes power calculations for the overall system, torque, speed, and linear speed for each axis, the time for a 4-foot layer, and the maximum mass that would allow for motion.
As a second-year project, we made significant changes. We changed components of all 3 axes and made the print area much larger. The updated design also allows for ease of assembly. It allows for a 2-man operator team to build the mechanical portion of the assembly in less than 30 minutes. Our Our new base utilizes a cart system that runs along angle iron and utilizes a rack and pinion design. This is a major improvement upon last year's, which used a direct drive. The rack and pinion allows for more precise movement and is relatively debris resistant. Our vertical trusses utilize a ball screw. The ball screw allows for about 4.5 feet of translational movement in the vertical direction. This far surpasses last year's design and meets our requirement of 4 feet of translation. Our MVP, otherwise known as our Y-axis, also utilizes a ball screw and houses the nozzle slider where concrete would be able to be printed. This is the nozzle slider assembly that runs along that Y-axis. These are the brackets that we used and fabricated for our vertical and horizontal truss. We have brackets for our motors, our frame brackets that attach the ball screws, and the housing connection bracket. These are our 3D printed parts, which include our X-axis, Y-axis, Z-axis limit switches, and our board housing.
Here's our Duet 3D motor control board, specifically the 6HC model. We have 6 driver ports, but we only need it for 5 motors to drive our axes. We have 9 input-output ports, but we're only going to use 5 of them, 1 for each of our homing switches to start the printer in a known location. And then over here we have our input power, which we have a 48 volt DC power supply, which is the top range of our board. And that's going to be powered by a 120 volt AC power outlet, which is a pretty standard outlet to find. Here's our full electrical system diagram and how it connects to our Duet 3D board. We have our 5 motors connected to our 5 motor drivers. We have our 5 limit switches connected to our 5 input-output ports. And then up here we have our interface with the computer and the user to implement our G-codes. Here's how specifically our homing switches connect to our board. We will be utilizing the input-output port and then the ground. And per the schematic sheet for the homing switch, we're going to align it to the normally closed port. Here's how our motors connect to our motor drivers. We have 2 related windings connected to the Alpha 1 and Alpha 2 ports, and then the other 2 related windings are connected to the Bravo 2 and Bravo 1 ports.
The board has built-in software and firmware. So the screen you see on here is Duet Web Control, which is supported by the board. Duet Web Control is an easy-to-use browser-based interface, and all it needs is an IP address. You can generate an STL file using SolidWorks and then upload that onto here when you slice it with Ultimate Cura. That sliced file is just uploaded through the upload button on the Duet Web Control.
Through testing, we have verified all of our requirements. This includes testing indoors and outdoors for our environment conditions. Each truss weighs less than 50 pounds and our assembly takes less than 60 minutes. We've created a rail system that has tolerances within the 5mm tolerance requirement. All 3 axes can be synchronized and our vibrations in operation are minimized. We have safety measures, including emergency stops on the board and the software. And our print volume exceeds the 4 foot by 4 foot by 4 foot dimensions. Our system utilizes 120 volt input power from an outlet that provides 48 volts for our board. The board is easy to use and utilizes open source software. Our controllers also G-code compatible, and all LEDs provide operation information. We also receive warnings on the Duet Web Control if there is an error.
Thank you for watching this video on our project. We are very excited to see you on Design Day.